Quantum computing is a rapidly evolving field that promises to revolutionize computation by harnessing the principles of quantum mechanics. Among the many approaches to building a quantum computer, topological quantum computing (TQC) stands out as one of the most exotic and potentially robust against errors. It is based on the fascinating concept of topology, the study of shapes and their properties under continuous deformations, and employs anyons, exotic particles that exist only in two-dimensional space. In this deep dive, we will explore the intricacies of topological quantum computing, why it matters, and how it could lead to a future where quantum computation becomes practically feasible. 1. The quantum computing landscape, challenges and the need for TQC. Classical versus quantum computers. Classical computers rely on bits, zeros and ones, to process information. Quantum computers, on the other hand, use qubits, which can exist in a superposition of states, allowing them to perform massively parallel computations. However, today's quantum computers suffer from noise and decoherence, external disturbances that cause qubits to lose their fragile quantum states. These issues make quantum error correction a crucial yet challenging aspect of building a scalable quantum computer. The problem of noise and decoherence, superconducting qubits, like those used by Google and IBM, and trapped ion qubits, used by IonQ and others, require extreme precision and shielding from their environment. Even the slightest disturbance, thermal vibrations, electromagnetic fields, or cosmic rays, can introduce errors. To solve this problem, researchers have proposed a fundamentally different approach: topological quantum computing. Instead of relying on delicate quantum states stored in physical systems, TQC uses topological properties of special quantum states, making them naturally resistant to errors. 2. The foundation of topological quantum computing. The role of topology. Topology is the branch of mathematics that studies properties of objects that remain unchanged under continuous deformations, like stretching or twisting, but not cutting. In TQC, quantum information is stored in topological properties of special materials, making it robust against local errors. Imagine tying a knot in a rope. If you pull on it or twist it slightly, the knot remains intact. But if you try to untangle it, you need a deliberate sequence of manipulations. This is the core idea behind topological quantum computing. Information is stored in knots of quantum states that cannot be easily disturbed by noise. Anyons, the exotic particles of TQC. In classical physics, we deal with two types of particles: fermions, e.g., electrons, and bosons, e.g., photons. However, in certain two-dimensional quantum systems, a new type of particle emerges: anyons. Anyons exhibit fractional statistics. Unlike fermions and bosons, their quantum states change in unique ways when they are exchanged around one another. The most exciting property of certain anyons, called non-abelian anyons, is that their history of motion determines their quantum state. By moving these anyons around each other in specific patterns, called braiding, one can perform quantum computations. This process is highly resistant to noise because small perturbations do not affect the topological nature of the system. 3. How topological quantum computing works. Braiding and quantum gates. In a topological quantum computer, qubits are encoded in pairs of non-abelian anyons. When these anyons are moved around one another, they perform logical operations on the stored quantum information. This movement is known as braiding. Unlike traditional quantum gates, which require extremely precise control of electromagnetic fields, braiding operations are topologically protected. Small errors do not affect the outcome, making computations inherently fault-tolerant. The role of Majorana fermions. One of the most promising candidates for realizing non-abelian anyons in the lab is the Majorana fermion, a particle that is its own antiparticle. Majorana modes can emerge in special superconducting materials, and researchers have been actively investigating them as a foundation for topological qubits. Microsoft Station Q research group is heavily invested in Majorana-based quantum computing, as it could provide a more stable platform than existing superconducting or trapped ion qubits. 4. Advantages of topological quantum computing. Fault tolerance. Because quantum information is stored in the global topological properties of anyons, it is highly resistant to small disturbances. This could significantly reduce the need for complex error correction mechanisms, making large-scale quantum computers more feasible. Scalability. Topological qubits are expected to be more stable than other types of qubits, meaning fewer qubits would be required for error correction. This could lead to a more scalable architecture for quantum computers. Long-term stability. The topological nature of computations means that quantum states remain stable over longer periods, reducing the risk of decoherence, a major challenge in today's quantum computers. 5. Challenges and the road ahead. Despite its promise, topological quantum computing is still in its early stages. Some of the key challenges include experimental realization of anyons. While theoretical models predict non-abelian anyons, unambiguous experimental proof is still being sought. Engineering the right materials, creating stable platforms for Majorana fermions and other exotic particles remains a significant hurdle. Scaling up the system. Even if we demonstrate a few topological qubits, scaling them into a full-fledged quantum computer is a daunting task. Several major research groups, including Microsoft, Google, and academic institutions, are actively pursuing breakthroughs in topological quantum computing. If successful, TQC could provide the foundation for a practical, error-resistant quantum computer that outperforms classical machines in solving problems ranging from cryptography to materials science. 6. The future of topological quantum computing. If researchers can successfully implement TQC, it could lead to a revolution in computing. Some potential applications include breaking classical encryption. Quantum computers could factor large numbers efficiently, posing challenges for classical cryptographic security. Simulating quantum materials. TQC could allow precise simulations of molecules and materials, accelerating drug discovery and materials science. Advancing AI and optimization. Quantum algorithms could optimize complex systems, from logistics to machine learning. While still theoretical in many aspects, topological quantum computing represents one of the most intriguing and potentially game-changing directions in the quest for a quantum computer. Topological quantum computing is not just another incremental step in computing. It represents an entirely new paradigm, drawing from deep mathematical principles and exotic physics. With its inherent robustness against errors, it offers one of the most promising paths toward building scalable quantum computers. Though challenges remain, the excitement around TQC continues to grow. If successful, it could redefine what's possible in computation, solving problems beyond the reach of classical computers and unlocking new frontiers in science and technology. The quantum revolution is coming, and topology may hold the key to unlocking its full potential.